Hello, this is Jinhyeong, Jung, and Jinhwan. Our topic is the anomaly detection model using the score-based model. In industrial problem, we encounter a lot of situations where we need to detect anomalies. We have deep generative models like Anomaly has been successfully applied to anomaly detection, even if the normal samples were only given in the training process. However, recently, the likely-based model is known to fail detect anomalous samples or OD samples. So we evaluate how well the score-based model can detect anomalous samples. So in likely-based anomaly detection setting, we can face anomalies with high enough likelihood. And these cases can be handled by controlling the thresholds. But to overcome this problem, we suggest a way of contextual likelihood examination, which examines the conditional likelihood of given data to find anomalous samples. And this is the explanation about the contextual likelihood examination. You can separate our given image X as anomalous region and the non-anomalous region. So you can factorize the likelihood of X as follows. From here, you can see that common likelihood-based model will classify X as a normal if log Px is high. But this likelihood can be dominated by a high log Px B value while having really low value of our conditional likelihood. So our idea starts from the expectation that the conditional likelihood should be low if the given image is anomaly. So our methodology will only consider the conditional log likelihood, which we will call as contextual likelihood.
Here we introduce the background of model. The first one is denoising diffusion probability model. The forward process destroys the data distribution using Gaussian Markov chain. And if the diffusion steps are sufficiently small, we can reconstruct the data using the reverse process using Gaussian kernel. Given forward process, it runs the reverse diffusion kernel via maximizing the following elbow. Here, the epsilon in the elbow term can be regarded as the score of part of the data distribution. And the optimal network epsilon set star matches the score of true density distribution. When we sample the data, we utilize the pre-trained score network using following form in equation 1, and it resembles to the Langevin dynamics. In previous DDPM, it sequentially corrupted the training data and learned to reverse the corruption. We can call it as denoising process. And the idea extends to the continuous corruption, which is given by Ito diffusion SDE in equation 2. When the f and g functions are linear functions, we can derive the reverse process from the given forward SDE. We can see that in equation 3, we should know the score function of the true density function. We approximate the score, the true score via training score network in the same area of DDPM, but we extend the time step t to the continuous space. Here is an overview of score-based generative modeling through SDs. In forward SD, with given f and g functions, we perturb the true data distribution to the distribution whose sampling is easy. In this case, we use the Gaussian distribution, and using reverse SD, we can reconstruct the data distribution. And we can connect the score-based SD with the neural ODs because every diffusion process can be represented as a deterministic process in a Liouville form. So we named the above ODE as the probability flow ODE, and we will use this form to compute the likelihood. And when you see the neural OD's paper, they suggest a way of calculating the likelihood when we have the dynamics of X corresponding to time step t. We can calculate the PXT by solving these ODEs. We now introduce our method. Here we introduce how we separate the imaging into normal and abnormal region. First, we postulate that the pixels whose deviations from original image and denoised image are big would be more likely to be anomalous pixels. So we denoise the image by taking forward and backward process sequentially, and we made the ratio of normal region to be 80%. After separating the images, we now calculate the probability of anomalous region given normal candidate region. We made the new SDs by taking restriction of dimensions, as you can see in equation 6. Similar to equation 5, we can derive reverse SD and express in a Liouville form. Remaining part is to get the score of the conditional likelihood in this equation 7. Computing the score of conditional likelihood is intractable. So we approximate PTZT given omega delta x0 equals y as follows. Finally, by concatenating z and mu omega delta y and giving these to our estimated score function, we can derive the score of conditional likelihood, and you can find similar derivation at the original paper whose name is the score-based generative model through SDE. From derived probability flow ODE in equation 7 and score approximation of equation 8, we can compute the desired conditional likelihood by solving the ODE in equation 9.
Now we'll introduce how we implemented our method. For training, we used SOBP for forward process. It showed best performance in the original paper. For score function, we used the wide ResNet, the backbone of the pixel CNN. It is also used in the DPM. We only used normal samples for training. For test process, test set contains both normal and anomalous samples. We used ODE integrator implemented in PyTorch library. As introduced before, we need to separate given images into normal and abnormal regions. So we take forward process from 0 to 0.15 times t, and then take reverse process reversely. In taking reverse SDE, we used Euler-Maruyama discretization, which is SDE version Euler discretization. And we used MVTech AD dataset, and it contains 15 categories. This image shows how our image separation algorithm works. From top to bottom, there are original anomalous images, reconstructed images, and anomaly likely pixel map, respectively. This is our method's result. We evaluated our model based on the AURC score. The first and second columns show the AURC score based on likelihood scoring, and the third one shows the AURC score based on reconstruction error scoring. Overall, we can see that reconstruction error based on anomaly detection method is superior to likelihood-based anomaly detection. But for some cases, likelihood-based methods show better performance. Also, we could find that conditional likelihood-based method is better than naive likelihood-based method. Especially for metal node dataset, conditional likelihood method made density scoring better than reconstruction error-based method. As far as we know, it is the first trial to detect anomalies using score-based model and find a way of conditional likelihood within the image. You could see that score-based model successfully works on anomaly detection. But likelihood calculation takes much more time. We can also utilize this model to inspect the imputation model. Thank you for listening.